case in question. And that's why it says here, endo product is generally the major product. That generally in there is to account for exceptions, such as here, where we've got two substituents on the end of the alkene and an sp3 center linking the two ends of the diene. If you've got an open diene and a single substituent on the dienophile, then almost always the endo will be the favoured outcome. But if it isn't, at least we can start to explain it by arguments like that. There is another steric, another steric effect in the diene that we need to think about. For the open chain diene to undergo a Diels order cycloaddition, it must adopt a certain conformation, what's called the S-cis conformation. I've been drawing dienes like that for the Diels order reaction, just because that is the way that you need to draw it to draw the mechanism sensibly. But I'm not saying that this S-trans conformation, it doesn't exist. In fact, in most cases, that will be favoured. But in most cases, the energy barrier between these two is so small that under the conditions of the Diels order reaction, the center so-called single bond in the diene will be able to rotate easily, and so the conformation required for the cycloaddition will be easily obtained. This would explain why cyclopentadiene on the whole is very reactive in Diels order reactions, because it's locked in the S-cis conformation by that sp3 center between the two ends of the diene. In fact, cyclopentadiene doesn't really exist at room temperature on its own. It dimerizes. So if you buy it, you buy the dimer of this, which is where one molecule acts as the diene, and another molecule, one of the double bonds, acts as the dienophile, a bit like I showed butadiene itself dimerizing. But this dimerizes very rapidly, and if you ever want to use this in a reaction, you have to warm up to 60 or 70 degrees the commercially available dimer of cyclopentadiene to get some of the monomer, and you can kind of distill it out and use it, but you must have something to react with it straight away before it re-dimerizes. So that's a very fast diene in Diels order reactions, such that you even have to make it from its own Diels order product before using it. There are some cases where dienes are unreactive, either because they're slow to reach the S-cis conformation or are just unable to reach it for steric reasons. So here's cyclopentadiene. If we set the relative rate of that in Diels order reactions to be 1, then if you stick another methyl group on one end, then that's about 1,000th of the reactivity in Diels order reactions. So if you were to take the same partner, the same dienophile, and do the check between these two, if this is rate 1, that will be rate 1,000th. And then if you have a butadiene which has two tertiary butyl groups at the two internal carbons, that's the opposite extreme to cyclopentadiene. That is essentially unreactive, because these two T-butyl groups do not want to be next door to one another in the S-cis conformation. Likewise, you can think of other cases. So this is pentadiene with a with an E double bond at the end. But if you have a Z double bond, and especially if you have a Z double bond at each of the two alkenes, then that again is also very unreactive, because it would want to be in the extended or S-trans conformation. So these are just a few examples to show, but if it's difficult to reach the S-cis conformation, the reactivity goes down. But that just makes sense pictorially. It can't reach the geometry required for the transition state. Right. Okay, so I think this is coming towards the end of what I've got in this session. This is just a little bit of a help for you in drawing stereochemistry for the Diels order. This is not meant to be an accurate representation of the transition state. This is, how would you go about drawing it? Well, one useful way of doing that is to just draw, it's not quite a cube, I suppose it is a cube really, draw a perspective box like that, and then stick your diene on the top and your alkene on the bottom. As I say, this is distorting it, but it's just trying to put things in the right places. And then you have ready-made indicators, these edges of the box, to show where the bonds would go. And you can use curly arrows, shown in purple here, to show how the electrons rearrange. So these two come down here to form a sigma bond, this pi bond comes here to form a sigma bond, this pi bond goes there to form the cyclohexene pi bond. And of course I could have drawn those arrows going exactly the reverse and come with the same result. Now, of course, this is distorting the geometry, but it does, and here is effectively what it's a bit more, in a little bit more realistic dimensions. But I think this is a good way of thinking of how am I going to draw this in 3D if I'm not really an artist. Draw a pretend box and then put your bits onto it. But if you're happy drawing something like that without having to draw a framework to put it on, then that's fine. So that's it. That's got it in a box. This has got it in a little bit more of a sort of a little slightly more accurate representation. So it's drawing the plane of the diene, and then the plane of the dienophile with its substituent. So the plane of that, and then mimicking the planar diene with a substituent up here. You need to try and position it such that the reacting centers are above one another, and that's where the box picture helps. The box picture also helps to visualize how the transition state in the middle here and the product, at least until it unfolds, are a bit like a boat cyclohexane. So here's the sort of a boat cyclohexane with the sort of prow and stern here, rather than looking like a chair cyclohexane. And I did mention that sort of looking like a boat cyclohexane in the previous session, I think. So this would be if you were given this plus this, and you were trying to work out what the geometry was of the product, then you try and set it up in one or other of these various ways. You can try it. This is another way of doing it, but it's a little bit more difficult to do unless this is in two colors, which helps, but this is actually picturing, just really effectively looking down from on top of the reaction, and it's trying to picture the diene with its substituent in this sort of orangey color, on top of, in blue, the dienophile. And it's showing it in the endo form, so the substituent on the dienophile is underneath the back end of the diene that's going to become the ene in the cyclohexene. As I say, that that picture can get more confusing, and it's also a little bit less clear as to where the new sigma bonds are being formed, because they're kind of foreshortened in this picture, there at the top and here at the bottom. But whichever way you do it, of course what you're trying to work out is what the relative stereochemistry in the product is going to look like. So here, this is two substituents on one face of the cyclohexene and the third substituent on the opposite face. And you can see that from this, or from this, or from this. So any of those ways of drawing it, whichever way you find easiest, will get you to the right result when you kind of effectively unfold this, or kind of turn this over so that you can draw it as a flat-looking six-membered ring. I think that is the end of that. Okay, so that's all I want to say in details about the Diels-Alder reaction. When we do tomorrow, when I finish the pericyclics lectures, we've got two more sessions this afternoon and one tomorrow, then we'll have a tutorial which will have some unseen problems in it, and you can see how you could work through some of these for yourselves, I hope. Okay, so that's the end of that, and I think that's lunch break now. Okay, so if anybody's, so we're finishing before we said we would, because I think about an hour's lecture is, or just under an hour is, I think, about right for attention spans. So I'm going to stick around for a little bit if you've got any questions. So any questions while we're all seated, or you can come and chat with me in a moment.
So can you explain the endoselectivity again?
With explain that?
Endoselectivity. Will you explain the endo product favor?
Yeah, okay. Let's go back slightly. Okay, so what we're saying is that what I think is the best way of explaining it is that there is a good orbital overlap between a substituent on the diene, in fact, if you like, it's the first atom substituted on the diene. I keep saying it the wrong way around. The first is the substituent on the dienophile. I apologize if I say these things wrong. And it's basically the first atom of that substituent. And what you're looking at is can that interact with the back end of the diene, with one of those back carbons that's going to actually form the alkene in the product? Can you get a good interaction there? So we've drawn this so that the 2 pi component here and the 4 pi component there, that's the LUMO, that's the HOMO. I could have reversed those, but it would produce the same result. So I've set it up so that the bonding interactions for the reaction to form the 2 new sigma bonds, which should be that one there and that one there, are set up to be favourable. When you do that, this HOMO of the butadiene itself here has this phasing of the next carbon along in the substituent, and that matches, has a favourable interaction with this carbon in the LUMO of what is being the diene component in this reaction. So I should really have an extra positive overlap. It's not really bonding because it's never going to form a bond, but I'm using bonding in the sense of constructive or good overlap. And we're saying that that favours kinetically so lowers the energy of the transition state, is another way of saying it, of the endo one, despite the fact that it's sterically more crowded by this substituent being kind of underneath the back of being close enough to have that interaction. So for the kinetic product, the fastest form product, secondary orbital overlap, which is what we're calling that, because it's not the one that's going to form the new sigma bonds. It's the secondary overlap. That's what's whoops, too far. That's what's controlling it. And here it is again. So, for example, here the endo is favoured over the exo. Endo, that's underneath or closer to the back end of the diene, which ends up as the ene in the cyclohexene, rather than away from it as in the exo. So here's again that orbital picture that in the endo, here's in this case I've got the LUMO of the dienophile and the HOMO of the diene, but it will come to the same result. Set it up so that the bonding you want to form, the sigma bonds, is looking good. And then here's the first atom out in the substituent, it's the carbon of the carbonyl group, and it has a good interaction with that back lobe of the HOMO of the diene, as opposed to the exo, where that substituent, then the carbon of the carbonyl group of the ester, is away from the back, so it's not underneath, it's away from the diene altogether, and so you can't have any extra interactions with the non-participating orbitals here. So endo is, by this interaction, lowering the energy of the transition state, you will get this being the kinetically formed, or the fastest formed product, even though that might be the more stable product. The only exception to that is, as I say, in a case where the reaction is easily reversible, where you don't have to heat it much to get it to reverse, then you may find cases where you end up with a sterically less demanding exo case, where the substituents are well out of the way of being underneath the back end of the diene. In fact, I don't know whether you do that here, but this is done as a second year undergraduate lab experiment in my university and in many in the UK actually, where you take these two and you warm them up enough to get the reaction to go at all, and you end up with this product, and then you stew it up a bit more, and you end up with a different product. So you take it, and you get the same. If you take the first product, you isolate it, put it back in, and heat it up more than you did originally, and you go to that one. So it shows it's reversing across here. So it's this secondary overlap that is favouring the endo. Now, I said that you could start thinking about electrostatic arguments. I won't dwell on that because I don't think it's as universal or as I don't think it's as useful as the secondary orbital overlap. Does that help?
Sir, can you please explain the electrostatic argument?
The which argument?
Electrostatic argument.
Yeah, I don't like it, but I will. Because people have produced this. Yeah, there may be a contribution from this, I don't know. What they're saying is, you need a particular case for this. What they're saying is, let's think about this one, cyclopentadiene and the methylpropenoate, methyl acrylate. What they're saying is that if you have the exo form, it's not disfavored because it can't have secondary orbit. Well, sorry, they're not perhaps denying secondary orbital overlap, but they're saying that repulsion between the delta plus carbon on the carbonyl group and these delta plus hydrogens here is disfavoring that. Whereas keep these two far apart and relative between these two, this will be favoured. This one's disfavoured, which means that this one must be favoured or must be preferred. And then you can start doing that with the others as well. I don't find that quite so satisfying overall. Prof. Singh wants to say something.
But hydrogen bonding is not playing any role.
Yeah, you see, you could argue, there is a hydrogen bonding interaction here, so there's a CH bond, it's a fairly acidic hydrogen, so you could make arguments about that. I only put this in because it's out there in the literature. Now I think about it, I could perhaps have left this slide out. That would have solved the problem, wouldn't it? But yeah, I don't really like this because I think this is stretching a point. I think this is, you know what the answer is going to be, so you're looking for anything that will support your argument. Whereas I think that I'm more happy with this. That seems to follow everything else that we've been saying about these pericyclic reactions. If we're going to explain more in orbital terms, then I quite like the fact, or not, I like the fact, it is generally preferable, I think, to continue with this orbital model. That's the preferred way of it. The experimental result is there, but in most cases the endo form is generally the major product. Say, where there is a pi conjugating substituent, in other words, where the substituent on the dienophile has got suitable orbitals to overlap. So that wouldn't apply if that was just a methyl group, for example, then that wouldn't be a great Diels-Alder reaction. The reactivity is increased and the rate's increased by having a conjugating withdrawing group here. Most of my examples have had a carbonyl, all of mine have had a carbonyl there. Anything else?
So in the slide where you've shown the temperatures and
Oh right, yeah.
sir, in that slide I have it
Um,
in the electron withdrawing groups and electron donating groups. It's
Okay.
before this.
Oh right, okay. Yeah, that's a while back, wasn't it?
Yes, sir.
Okay.
So actually in the fourth reaction, that one with 120 degrees Celsius and 6 hours. And sir, in that previous reaction, so why is there so much gap in the hours? Like the first one is taking 0.5 hours and this is taking 6 hours.
Well,
Like why is it taking so long?
I don't know. The other thing I don't know is if these are the minimum conditions or these are just some reporting conditions. Right, between these two. Okay, yes, of course. Right, this is dying with no substituent. Oh, you're saying why isn't this one faster? That's a good question. It would be. I think what would be interesting is if this lower one was heated to 150 degrees, to see what difference that would make in terms of the reaction time. And maybe that if you heat it to 150 degrees to make a proper comparison, then it may be that either the starting materials or the products are prone to decomposition. So it's not really a strict comparison, is it, with a 30-degree temperature difference? Because 10 degrees difference is supposed to double the rate of reaction, isn't it? So, yeah. So if you were to go to 150 there and the compounds survive that, the starting materials, then I think it will be much more comparable.
But on the left-hand side, it is okay.
Sorry?
On the left-hand side, it is okay if you compare the two.
Oh, actually across here, yeah.
The upper, first one and second, on the left-hand side.
17
Oh, these two, yeah. I think that's much more noticeable, yeah. I think we're talking here about the effect of substituents. Any conditions I've put on here are a little bit selected at random. You can find that there are so many examples out there in the literature. I guess that's just to put some realism into it. And I'm sure if these compounds survived at 150 and the product did, then this would come down dramatically, I think. Just these are reported results. So, but they give an indication. I think this, if you look at, I suppose the real point I'm making here is that the substituents dramatically affect the rates. And so from no substituents to the most favourable set, you can see that makes a big difference. Yeah. In fact, here I didn't. But if you think about this one, okay, cyclopentadiene is pretty reactive, but this goes, in fact, you have a job stopping this reaction. So, yeah, these are not all strict comparisons I've got here.
Excuse me, sir. In the second reaction, where the conditions are 120 degrees Celsius in 6 hours, the gap between HO and LUMO reducing now.
Sorry, say that again.
The gap between HO and LUMO being reduced
By having the two substituents on. Yeah.
That's why the conditions are.
Well, that's why it's. No, I think what was being said was, why is this not shorter than 6 hours? The thing with a lot of these, when you see reported results like that, is you have to actually put some human touch into it. Now, did it take 6 hours, or did someone monitor it after 6 hours? You know, when you see, it's classic. If you see a reaction takes 18 hours, that means they put it on before they went home, and then took it off next morning. It doesn't mean it needed 18 hours. It might mean that after 18 hours the material is still there. So you have to, with some of these things, you have to be you can't make strict comparisons unless you know the two reactors were done side by side by the same worker at the same time in the same labs and so on. Yeah. So I think I wouldn't worry. You're not meant to be too interested in the details here. You're interested, I mean, as Professor Singh said, you're interested in dramatic change here, and in the fact that compared to that, all of these reactions go much more easily once you put a substituent on there, or substituents on there. Of course, this is a substituent in the internal position of an alkene. That's at the diene. That's the terminal position. That makes a difference too. As you see with the orbital arrangements, the substituent has a different effect on the orbital, on the HOMO and LUMO, depending on whether it's on the end of the diene or on the internal position. But nevertheless, a donor substituent will, on the diene, will be more favourable than no substituent at all. How are we doing?
Sir, in last slide.
The very final one.
Last slide.
Yeah.
How we predict the given product stereochemistry के whether the substituent is below the plane or above the plane?
So this one.
Last. That is.
This one.
Yes.
The way to predict where things are going. But the way to predict where things are going to be is just to draw them out like this. I like the box model because I think it's less, it's easier to construct and less likely to go wrong. And then you have to imagine opening it out. So if you imagine taking this folded product, then if you think about it, if you open it out, this methyl is going to come up, this hydrogen is going to come up, so the aldehyde is going to go down, this hydrogen is going to come up, so the acetate will go down. You have to, this is the issue with stereochemistry, 3D drawing in 2D, you have to imagine what would happen when you unfold it, really. Yeah. Well, the same here. If you were to open, here's your sort of folded structure. You have to think that if I unfold this, then the methyl, that hydrogen, and that hydrogen are all going to be on the same face. Because as I open this out, this acetate is going to go this way. This hydrogen is going to come up to be on the top face. So this acetate will be below. This aldehyde will be below, and this H will be below. Acetate down, aldehyde down, H down. There's nothing magic scientifically there. It's just about your perception, imagining what happens when you unfold it. But in all cases, the stereochemistry in the original components has been maintained. So I'm starting out here with an E double bond here, and that's still, I have to draw that E here, or E here. So you translate your original starting materials into the same geometries in the transition state for the reaction, and then see how that maps through onto the products. And these are three alternative ways of trying to draw it. So it's, if you like, it's this translation we're trying to make. And all I can say about that is you have to practice it. Try drawing some examples that you can find in the literature and seeing if you can make that transition, or see if you can do that unfolding, shall I say, to make it work in the same way as authors in scientific papers have said. But watch out in case they say this gives the expected. If they say this gives the expected stereochemistry, that's fine. But you can always find cases where, for whatever other reason, with other groups around, they may go differently, and so you have to watch out if they say this gave the unexpected product, then anything you do here won't necessarily translate in the same way. I have to say, if you think of anything else that you need to ask about, then please ask any time you can find it during the day. I'm not going to hide. Well, I hope not anyway. Okay, so I think that's it for this morning, and we'll start again, I think, at 2 o'clock, Professor Singh, isn't it? What time are we due to start this afternoon? I forget.
Okay, so we will have lunch, the same place where we are going to be, and the next session will start at 2 o'clock.
2 o'clock.
2 to 3 and
So this afternoon we'll have 2 more sessions.